All right, so the lab we're doing today, we're going to investigate what the effect of radius is on speed. So the formula that we're investigating today is this one. Okay, V equals 2 pi r over t. Okay, so if we're looking at that formula, the relationship between radius and speed should be fairly clear. Okay, so what we're investigating is what will happen as radius increases to speed. Okay, so in this lab, what we're doing is increasing or changing the radius of the object moving with circular motion and recording the corresponding speed for different radii. Because it's not radiuses, it's radii. Okay, like hippopotami, not hippopotamuses. Okay. All right. So, in talking about the design part here, okay, obviously we've talked about what we're changing and what we're hoping will change in response to that. But there's a few things that probably need to stay the same, because if we start thinking about all the things that can affect speed, a few other things come into play here. Okay? If they're not working, put them on the top, guys. Okay? They gotta get those bells figured out. Okay. These are some other things that could affect speed. Agreed? Right? Because speed is also in this formula, and this formula also applies to something moving with uniform circular motion. So some of the things that we might want to, control might also be in that formula. So here's how this is going to go. We are going to have an apparatus like this. Okay, so you are going to have a piece of PVC pipe that you will be holding on to. That's the only part of this apparatus that you will hold on to. Okay? You need to make this rubber stopper move with uniform circular motion at different radii of a circle. Okay? What's the purpose of the mass hanging underneath?
For the centripetal force?
Exactly. It's providing the centripetal force. Remember, that's another one of the things that can affect the speed of the rubber stopper. I can't just hold the string and whirl this thing around and around and around. Okay? If I do that, do I have any idea what the centripetal force is? None. Okay? But if I don't hold the string, the only thing that's keeping that thing in the circle is the mass. Well, what in particular is working on the mass right now? Gravity. Yeah. Okay, something to think about. That might also be part of the analysis. So, okay, keep that in mind. All right. Now, you see what I'm doing here? I'm not holding on to that string at all. Okay. If I want to go in a smaller circle, okay, I have to be very careful about how I do it. I have to maintain that radius while this thing is going around and around. I make it look easy because it's not my first time. Okay? The first few times you guys do this, it will be a bit difficult. Now, also notice that my circle is fairly horizontal. Yes? Mm-hmm. There's a real tendency for people to do this. Because they don't want to get it in the face. Okay? Is that a horizontal circle? No. Look at the speed of my rubber stopper. Is it very uniform right now? No, and I want it to be nice and uniform. Okay? So what you're going to have to do, and you want to pick someone to be the whirler, and you also want to use a better side. This has got a big groove in it. You guys probably see it catching as it was going around. The other side of this is much smoother. Okay? but none of them are perfectly smooth. Because I cut them, and I suck at all things craftsmanship. Okay, like, we had a set of coat hooks fall off the wall last night. It took me an hour and a half to get them back up. Okay, I know my limitations. Anything that involves power tools is not my wheelhouse. Okay, so you're probably thinking, Coder, you probably didn't need power tools for that, but that's what happens when you're not good at construction. That is, you start using power tools in places where they shouldn't be used. So just know that there's probably one side that's smoother than the other. Try and pick the smoothest side. Unfortunately, the smoothest side is not very level, because again, I'm not good with tools. I don't cut straight. Yeah, that's why I didn't go into construction. Okay, so just be mindful of that. Okay, find a side that's good and smooth and fairly level. Okay, but that could, be useful later in your lab report. Please don't list source of error, Coder's incompetence with tools. Okay, be more scientific than that. Okay, for your sources of error. Okay, is that making some sense? Okay, so you're going to have to whirl that thing around. You have to make sure it's fairly horizontal when you're doing it, and you're going to be doing this for different radii. Okay, so we're going to be looking at 20, 30, 40, 50, and 60 centimeters. But when you do your calculations, you want that in meters. Okay, so I'll bring the meter sticks out. Where do you measure the radius to? The center of the mass as best you can. Now, how are you going to know if you've maintained that 20 centimeters? Mark it on the string. Now, this is the trick. Where is it smart to mark it? Here, where you'd actually measure it to, or here? Yeah, okay, so measure that to be your 20 centimeters, and then mark where the bottom of the tube is. Because that's easier to see when you're whirling this thing around and around. Okay, so if I'm whirling this thing around and around in a circle and I've got my mark right here, it's much easier for me to watch that and not get the rubber stopper in the head. Okay, if I'm watching it up there, I have a tendency to lower it, which is fine at 20 centimeters, but at 60, you're going to get it in the mind, okay, pretty fast. So make sure that you are marking that distance further down on the string. Just take a board marker, they'll work just fine. We got lots of string, okay, so just put your marks on there and go with that, okay? All right, for our hypothesis, okay, so our if part of our hypothesis needs to talk about the relationship between radius and speed in this formula. The and part, as always, is going to describe the experiment. A rubber stopper will be whirled in a horizontal circle of increasing radius under constant centripetal force with its speed measured. Okay? Then tell me what's going to happen to speed as radius increases. Now, there's really only one issue with this experiment. And no, it's not safety in getting it in the head. Okay? That's obviously safety is always our second consideration. Okay? In the science department, we like to say convenience first, safety second. Okay? It's probably not a good rule to live by, but that's how we roll. Okay? So the thing to be mindful of is that how are we going to measure the speed? Like, one of our variables is speed, and we have to have a record of how fast this thing goes under various load.
Recording period, like recording it on your phone, seeing how many times it goes around in 1 second.
Yep, exactly. Okay, we're going to have to get the period of this motion. Okay? Now, here's how we're going to do that though. Okay? We're going to actually time a number of revolutions rather than try and time one revolution. Okay? That's going to bring in a whole bunch of error, right? Because you're going to be like, okay, started when the stopper was right there. So start and then stop. Not a chance. You're not going to get that on one rotation. Okay? So what we're going to do instead is we're going to time our, I think it's 20 revolutions. Yeah, okay, so you're going to time 20 revolutions. So once the person who's doing the whirling has got it under control, pretty consistent, okay, one person is going to be a timer and one person is going to be a counter. The person whirling is just the whirler, okay? That is their one job. They need their full concentration for that job, okay? So the other people involved have to do the recording. So once they're pretty consistent, okay, the timer can go and choose a starting point and say, all right, start, and then start counting. 1, 2, 3, 4. When you get to 20, stop the timer. Okay, now that's the time for 20 revolutions. Period is the time for 1. Okay, so what will you have to divide that number by? 20. Perfect. Okay, so here, just to make sure that we eliminate as much observational error as possible, each radius will be done twice, and we'll average the two. Okay, that helps to take into account that, yeah, we're going to have reaction time errors and things like that. Okay, so that'll take that into account. You'll have your average time, divide that by 20 to get your period, okay, and then calculate your speed using that formula. Okay, now, what should be the trend as we get a bigger radius?
The velocity should
Go up. Okay, so that's what we should see. All right, so for much of the analysis, all you're doing is filling in the chart. Okay, a lot of your analysis is just filling in the chart. Okay, number 4 is asking what was the force that acted as the centripetal force and determine its value. Do not use that formula to calculate that centripetal force. You already told me what was acting as a centripetal force, and there's a much easier way to calculate it than using all of the measured values you got in this lab. Okay? Think about it. Okay? You guys think about it. There's an easier way. Don't use that. Okay? For number 5, I want a graph of velocity versus radius. Okay? So manipulated variable on the x, responding variable on the y. Okay? And then tell me what the relationship is and explain. Okay? Doesn't have to be a super long explanation, just explain. Okay? And then for your conclusion, copy paste your hypothesis. Tell me was it accepted or rejected and why. Okay? Sources of error, not Coderre's craftsmanship, but anything that Coderre's craftsmanship could have affected can be listed as a source of error. Okay? And ways to improve it. Don't have Coderre build stuff. Okay? Have Mr. Kruger do it. And that's his wheelhouse, so I don't know. Okay? But same as always, you should have lots of time to work on the lab report here because the actual collection of data, once you get the hang of whirling this thing around and not having the circle go in and out, okay? That's the most time-consuming part of the lab, is having the person who's doing the whirling get the hang of doing the whirling. Okay? It's really easy for that circle to move. It's okay if it moves a little bit. So when you're watching that string, if it's going up and down a little bit, that's okay. If it just goes right up into the tube and you can't get it back, start over. Okay? If it's moved more than like 2 centimeters, start that trial over. Okay? It's fine. It's gonna happen. Okay? Just, you can start that trial over if it does. Okay? Again, maybe that's a source of error you can use. Okay? We're doing our best here, but obviously it's not going to be perfect. Okay, so as I said, you want to do your markings with the board markers. There's tons of them around. Just mark on the string when you've got your 20, 30, 40, 50, and 60. And so we said, yeah. Okay, and then 2 trials of 20 each. Okay, I will bring out the meter sticks here while you guys get the rest of your materials.